Yeah, that seems like it's working. All right, I'll just give people a second to sit down. But I will get started. It's 11:05 now. The recording started, so I'll get going. If I could have everyone's attention, please. This is an uphill struggle. All right, there's still a few people coming in. I'll give them a chance to sit down. Okay, let's get going. Welcome to day 2. For some of you, I think this will be day 3 if you had a Monday tutorial for COMP1511. So before I get going, let's talk a little bit about what I covered yesterday. So yesterday, in case you didn't make it, or you've managed to forget everything in 24 hours, so welcome to student life. That'll probably happen sometimes. Probably later in the term than now when you've got too much to think about at once. But still, we looked at the course admin. So we had an idea about what all the individual assessments and portions of the course are going to be, what it means to be in tutorials and labs, the kinds of things that we expect you to hand in, that kind of thing, and how many marks everything is worth. Hopefully you've also got a decent idea from what I was saying yesterday about some of the ways that you want to approach what's happening in this course. Don't worry too much if a lot of it is still, I have no idea what's going on. When you look at the code that I did yesterday, there's not that much of it yet. We're going to obviously be building on that today. We're going to add some more code. We're going to talk about some of the things that make up programs and how they work. I should probably go to the next slide when we're talking about it. So at least what we got to look at was, I opened VLab once at least. I showed you a few little commands we can run in Linux and one program that we looked at, and I think I've got that here. So we'll have a quick look at this again today, but we're probably going to go on and do more stuff than this. But let me talk about what we're covering today. So in the first hour, I'm going to talk about some of the things about how a computer remembers information. So remember yesterday I was talking about the basic theory of what a computer is if we're going to break it down to its sort of theoretical fundamentals, it has a thinking bit and a remembering bit. We're going to be talking about both of those today. Variables are the first thing that we're going to look at in terms of the remembering bit. So the bit of our programs that's going to store information for us to reuse. So there's the information that we can make changes to, we can reuse and stuff like that. Those are variables. We're going to do some really basic maths. There's no maths prerequisite or anything for this course. We're not going to be delving into, I don't know, matrices or differential equations or anything like that. Like literally the maths that I'm doing today is like, how do we do a division in code and how do you do a multiplication? So I'm pretty sure everyone who's gotten to this point to computer science has probably gotten through primary school maths, and that's kind of the limit of what we're looking at today. We can do a little bit of logic as well, so that'll be interesting. And we're going to look at the idea that computers sort of do maths in a different way than humans, and in a different way than how theoretical maths is done, because computers are limited in the fact that they do have to know and remember everything, which means they can't think very well about notions like infinity and stuff like that. But not going to go too deep into those. The second hour, we're going to look at ways in which our computer... Ooh, sorry, getting a little bit of feedback. I'll turn that down a little. Hope you can still hear me up the back, probably. Yeah, okay, getting some thumbs up. All right. We're going to look at how our computer decides what it wants to do. So as I said before, we're not going to tell our computer exactly what to do. We're going to give our computer the options to do what it needs to do. So we're going to look at the ability for our computer to basically say, I'm going to run certain bits of code, but not other bits of code, or I'm going to decide based on what I see at the time what I'm going to do. So this gives our computer and our programs the ability to to make decisions on the fly, which is one of the nice things about computers, is we get them to sort of assess the situation they're in and decide what they're going to do. So we're going to look at those today. And if we get time, we're going to make a little program. Actually, I'm going to try to make time for that little program so that we can tie a lot of this stuff together. And we'll see our first sort of genuine demo beyond the basics that we have. Okay, brief recap of what we looked at yesterday. Some of the components that we're thinking about here. Right up the top, the two lines in blue with the double slashes in front of them. Anyone remember what they are? I think a lot of people just said comments at the same time, so that's good. So all of that stuff is just basically information that goes to our other programmers or remind ourselves what's going on. We actually write a lot in our programs that's basically little messages to ourselves to remind ourselves what we're doing, and messages to other people. And it can make it much easier to think about your code if you've got some stuff in, like, just straight out plain English that you can understand. So the double slashes tell our compiler, the compiler being the thing that translates our code so that our computer can run it. The double slashes tell the compiler to ignore it. So it's for humans only. The computer doesn't run those lines of instructions. The next bit is the include standard input-output library. Don't worry too much about that yet. We are going to cover what they are and how to use them later. For the moment, we're just going to use it until we have a good idea about other parts of code and we're going to understand it. In here, our int main void here. Don't worry too much about that particular line. But that is what we call our main function, and that is the bit where our computer is going to start looking, where it starts running our code. So it's going to look for this main, and then it's going to look inside these curly brackets here. And inside the curly brackets, it's going to go line by line, one after the other, and execute whatever instructions we've written on those lines. This is where a lot of the work is going to happen in our programming. This is a lot of where we actually tell the computer what it is we would like it to do. This one's pretty simple. The first line is printf. Printf is actually taken from that standard input-output library. So what it will be doing is it will be saying, I would like to print out the words hello world. We're going to be using this a bit. Your second week tutorial is going to do a little bit of printf. And we're going to look at the other way that we can actually accept input from the user as well. So we're going to talk about a bit of that today. And then the line at the bottom is return 0. All that does is ends our program. We don't really have to worry too much about the 0, but it's a pretty old convention in C that we would signal back when the program finishes whether it was successful or not, and 0 was usually successful, and all other numbers meant to different errors and things like that. But we don't really have to go into that in too much detail because we don't use it that much. Okay, so I want to talk a little bit about how a computer remembers things. So when we boil down a computer into its actual physical pieces, most everything in your computer, like all the RAM and your hard drives and everything like that, is a series of little switches. If we took like a bank of light switches, there's not many light switches in this room. There's like one on each door. But if we had a whole bank of light switches and you can just flick them to on or off, that's basically what your computer's memory is if you were to be able to boil it down to a nanoscale and actually look at it and see it. It's a whole bunch of on-off switches that can be left in the on or off position. We call them bits. And bits, the word bit is short for binary digit. Binary meaning it only has two possible values, a 0 or a 1. And if we have enough millions and billions of these in our computer, we can flick them all to 0s and 1s, and then you can have, depending on how you sort of decide how to represent numbers and things like that with your binary system, you can then build up a whole bunch of information. But when it boils down to it, all it is, like, we can nearly think of as the only thing our computer can think in is 0s and 1s. And all it is just slightly more complicated combinations of 0s and 1s put together. So everything's going to be in these 0s and 1s we call bits. Usually to make things a little easier for ourselves, so that we don't deal with bits individually, we deal with them in chunks. 8 bits together is what's called a byte. Some of these numbers you will have heard of before, because when people talk about like internet speeds. They talk about megabit internet speeds and stuff like that. If you've got NBN and it actually stays connected, it's, you know, it's supposed to be in megabits and stuff. When you get sold a computer and you get sold a computer based on how much RAM it has on it, that kind of thing, you will generally get sold things in gigabytes worth of RAM. If someone tries to sell you something in megabytes worth of RAM, you probably don't want to buy it unless you're purchasing for a museum. But these things boil down to these kind of fundamental pieces. I was about to say fundamental bits and pieces. That would have been funny, but no. And these are chunks of information that we store. And so we're going to use them in different sizes depending on what it is we're trying to store in the computer. You may also have heard of things like 32-bit and 64-bit systems. I'm going to assume that pretty much all the computers in this room are actually 64-bit computers at the moment. You can actually look up in your computer specs. You can see whether it's a 64-bit computer. I don't know exactly where. Every operating system looks at it a different way. The 32-bit and 64-bit are kind of like how we work with the fundamentals in the computers. So whether the computer's sort of smallest unit of memory it looks at is 32 bits or 64 bits. I'm glossing over the detail here. You want to go into this, you'll see later in your degree and stuff, but I don't really have time to explain the entire history of how many bits a system has. Anyone ever had a Sega Mega Drive? Probably not, right? That's probably my era. Wait, someone's seen one? Yeah. That was a 16-bit computer, so it actually had a smaller kind of way of processing things. I'm glossing over it, right? You'll learn more about it later. Okay. A variable is a very common thing in programming. It's very fundamental to what we do in programming. A variable is what we do, or what we create when we're asking our computer to make something for us and we're asking our computer to remember something for us. So what we're going to be saying is, hey computer, I would like you to remember this number. And so I will give you a number. This is a variable. And maybe I'll change it later. That's why it's called a variable, is it doesn't have one value that it keeps forever. It can change its value. So we can give it different values. We're going to start with numbers. And when we say, computer, we would like to remember something in this variable, my computer will then say, cool, OK, you want this number? This number takes, I'm just going to throw a ballpark number out there, 32 bits of information to store this number. It will grab 32 bits of your memory. So your RAM in your computer will go, hey, RAM, it's not, they're not talking to each other like that, but you know, it'll go, hey, RAM, give me 32 bits of space because I need to store this number for the human to remember. It's not really the human, it's the program, but you know. So it will grab this piece of information and go, yeah, human wants to remember this number, so we will reserve this much memory for this number. We're going to go more into this later. We're actually going to be using memory explicitly and stuff like that as we go along. When we make a variable, it will have a particular size, and we will say, this is what we had in mind for it. So I'm going to show you two types of variables today that have two different purposes, and then you'll kind of get the idea about what the purpose is for it. So, oh, actually, they're right there. I love it when they're on my slides, and I think, oh, I'm going to talk about that soon. So, two variables that we're going to look at today are two different types of numbers. First one is an int. It's short for integer, which is a whole number. And so this can only have whole values, no fractions, no decimals, anything like that. And the other thing is called a double. I'll explain why it's called a double, but a double is a floating point number, which means that it has a decimal point somewhere in it. So that means it has the ability to do things like halves and just other decimal values, things that whole numbers aren't going to have. When we create our variables, we're always going to give them a name. And this is the reminder that half of our programming is going to be for people. And so this is something that we're always going to need to think about when we're making our variables, is we're going to make a variable so that we can use it again later in our own code. And if we're going to use it again later in our own code, we're going to want to remember what it was called. So sometimes we will pick things based on their function, pick things based on what it is they're representing. A variable name is usually a noun. I don't know if people are like, I don't know, some people go to computer science to escape grammar and English and stuff, but a noun is a word for an object. So For example, if I'm storing the answer to a question that I'm slowly building up, I could call my variable answer. If I'm storing the diameter or something I'm calculating, I might call it diameter. Things to avoid is single letter variables like A and B. It's really easy, 1,000 lines of code later to just look at it and go, what is B? And then you just be like, what's going on? Whereas if you look at it and you go, diameter, oh, I know what diameter is. It's going to be, obviously, the diameter of the circle we were working with at that point in time. There's a few little rules and conventions we're going to use with the variables. They're always going to start with a lowercase letter. And remember yesterday I was talking about the English teacher that won't like it when you get things slightly different with grammar and stuff like that? Here, C is a case-sensitive language, so that means upper and lower case have meaning in C, and they will be considered to be completely different letters. So, answer with a capital W, answer with a lowercase w, we as humans look at that and go, oh, it's just the same word, that's just a typo. Your computer is not going to be able to deal with that. Your computer is going to say, I don't know what those two things are, they're definitely different from each other. So just be careful with things like that. There are words that C has that we can't use for variable names. So you've seen some of these already, like the word return. Return was something that was going to end our program. It's not specifically going to end our program. The return has more ramifications than that, which I'm not going to tell you about now, but we'll talk about in a couple of weeks, I think. But either way, there are some C words that are reserved, and we can't name our variables after reserved words because our computer's going to say, I know that that has a meaning, and you're trying to give it another meaning, and that's confusing. Yeah, question? Yeah, if you were to capitalize part of those words, then that would be a different word. So if I did a return with a capital T, I could technically use that as a variable name. I would be really careful about using that as a variable name because it's going to confuse the hell out of a person reading it. Because return we think of as a keyword in C as well that we don't necessarily want to use for a variable name. But yeah, they'll be different as it is there with the answer and answer. Your computer will see them as different. Sorry, the question there was for everyone, because you probably can't hear necessarily, because I'm the only one with a mic. If we were to put capitals, random capitals in amongst those keywords, would they then not be C keywords? And the answer is yes, they wouldn't be C keywords there. If we think that we need to have multiple words for a variable name, sometimes, for example, I've got a long answer and a short answer or something like that. This is context we'll get a bit more of as we actually start using these things, but I wanted to tell you about it anyway. There's two ways of doing this. We can put an underscore between things, and that's going to give us a gap between the words, or we can put a capital letter at the start of each word in there just so that it's easier to read. You can use either one of these styles. The first one is known as snake case. It's like a snake that gets lower and taller. And then the other one's called camel case. It's like an animal with lumps occasionally in it. Don't worry too much about that. Generally, as we're going to do things, we will just stick with either one of these two, and we try not to swap between them because it's a bit confusing. Okay, the variable types that we're going to look at today, the first one is an integer. So the integer, I said every variable was going to have a purpose. It was going to have a certain amount of memory it used. Actually, that's all I really need to talk about. There's also ways that the variable actually carries its data. There's ways that it encodes its data. Not all of this is super important for you to need to know, but you do need to know that integer is a whole number. Integer being a whole number means it cannot store fractions. So if you put 1.5 into an integer, it won't deal with it entirely. I've got another slide. I'm going to talk about that in a second. Most commonly, and in everything we're going to do in this course, an integer is 32 bits worth of memory. 32 bits worth of memory means it does have a limit. So if you have 32 switches that can turn on and off, this is probably the most complicated maths I'm going to talk about today. If you have 32 switches that can turn on or off, you have 2 to the power of 32 possible values that you can store in an integer. You don't really have to worry about those, but I've written them up here. Like, to be honest, I had to go get a calculator to figure out exactly what they were, because I don't memorize these values. The only thing you need to know is that there is an upper value and there is a lower value. So there's 2 to 32 possible values going to negative and positive, and there is an end on either end. So if you just keep adding integers together, there's a point where they can't actually store more information going upwards. If you keep minusing them from each other, they can go off the bottom, and we can have potential issues there. But most of the time, we can store pretty much any value that we need, because most of what we're going to be doing is going to be around 0, going up and down in different directions. Most of what we're going to do in this course is probably not going to hit these limits, but if you don't know about them, there can be problems. So when an integer goes above the top limit or below the bottom limit, we call it overflow and underflow. This isn't super important. This is more like trivia that I'm telling you about, but it's also kind of handy to know about. What happens when we send a negative integer off the bottom? It will magically turn up at the other end at the top, and then it'll start continuing going downwards from the top. It's like, I don't know, like those really old computer games where if you walk off one side of the screen, you just magically appear on the other side of the screen, and back and forth and up and down on the top and the bottom. So it's not in any way realistic behavior for a number. It's just the way they're calculated, which is why we need to be at least aware that if we go off the end of the integer, things that are going to get strange. I got a question. The question was, is this to prevent the system from crashing? It's not necessarily to prevent the system from crashing. All it is that the integer just can't store that information, so it goes off the end and it just appears at the other end. If you want a little bit of trivia, look up the Ariane 5 rocket explosion. So this was a French heavy payload rocket. So like, you know, those big rockets of the 60s and 70s that they used to send people into space with and stuff like that. I think when they went from the Ariane 4 to the Ariane 5, they updated the size of the rocket, but they didn't update the telemetry software, which was controlling where it was going. And then with the bigger rocket, it was capable of getting numbers that were large enough to go off the end of an integer, and they had an overflow problem, and they went from like calculating minute changes to how they were aiming to suddenly trying to do a 90-degree turn in flight with a few hundred tons of high explosive fuel in it, and yeah. Hilarity ensued. It wasn't funny. But yeah, if you want to look it up, it's kind of interesting. Ints are most often going to be 32 bits. We're going to be working in 32 bits with all of our systems, but not every system is going to be 32 bits. Usually they're only going to be changing in legacy systems, but I'm going to assume that at some point in the future we'll probably go to larger bits values for integers. But for the moment, you can probably just go 32 bits for everything. Okay. Doubles are floating point numbers. Floating point means they have a decimal point somewhere in the number. So for example, here I've got two numbers up there, 10.567 or 105.67. You can see that the actual digits we're storing are exactly the same in those two numbers, but we've just moved where the point goes in amongst the digits. And that's why this thing is known as a floating point number. The reason the ones we're using are called doubles is because they store 64 bits of information, which is double the size of the integer. And it's actually double the size of the older variable that you can use for floating point numbers. Doubles also have some things that you do need to think about. So they have a bunch of digits, and they have a floating point somewhere in amongst those digits, which means that everything that they do, they will represent what we call a real number. Is everyone here doing maths? It's not called Maths 1A anymore, is it? Is it Maths 1A? It is called Maths 1A? Yeah. So is everyone doing that at the same time? I think some people are. Oh, there's some nods and some shakes of heads. It's okay. I don't know if they do this in high school anymore, the idea of real numbers versus integers and things. But a real number is kind of any possible number. And so something like a third is a real number. So it's just 1/3 of the value of 1. The issue that we get in C and other languages, and basically in computers in general, is if I take 1 and I divide it by 3, I can't get an exact third. Because as you may know, the decimal value for a third is 0.3 repeating, so the 3's repeat forever. If you try to repeat the 3s forever, our float's going to run out of digits eventually, and it's just going to stop and go, okay, no more 3s. We couldn't do any more 3s because we had 64 bits of value, and we've got 64 bits worth of 3s and a decimal point. So if we get that, and then we start multiplying that third by other things, dividing it by other things, and stuff like that, we can cause errors with the fact that we approximated the third. We didn't get an exact third, we approximated it, so we can get weird things happening. This is another thing, it's like the overflow and the underflow of the integers. It's something to know about, it's something to have a vague idea about, but in general, the way we're using these things is not super important. So what I'm doing today is I'm starting off with just showing you what these things are and a bit of background and some of the weird ramifications of it. If a lot of this stuff is mostly forgotten and you just remember there's two kinds of variables, an integer and a double, one's for real numbers and one's for floating point values, that's probably not a bad place for you to be in. So a lot of this stuff is slightly trivial information, but it may come in handy at some point. So here's some code for how we use variables. So yesterday I said we've got the curly brackets. It's what's inside the curly brackets is a series of instructions. So here I have some instructions that we might use for variables. I mentioned there's an int and a double. Did I? No, I only have integers here. You can see that the way that we are going to be working with these variables in our text editors, if we're using gedit, which a lot of people by now probably have used in the labs. I think we've had about a third to half of the labs so far, so a lot of people in here have probably seen something like this. Whenever you type something in a code editor, it tends to highlight it in a nice color for you so you get a good idea of what's going on. The int will light up green, which is reminding us that this is a C keyword that is going to be one of our variable types. So when I want to create an integer, I say int, and then the thing after it, I say the name of the integer that I would like to have. I used answer again here because it was the example I had before, but you can name your integers and doubles or other variables, whatever names you feel you need for your program. Remember, the names are for us and for humans, so you name it a way that you think is going to be the best understood as it gets used. So when I do that, my computer is going to look at that instruction and say, the program would like one integer with this name. So the first thing that it will do is it will look for the memory for that integer. So it'll go, okay, I need 32 bits of memory. It'll grab 32 bits of memory from the computer and go, okay, this much memory, this little chunk of bits, 32 of them, is going to be kind of reserved for use by this variable called answer. It is then also going to remember answer from then on. And you're going to be able to do things with answer. As I'm doing here, the first time I give an integer or a variable a value, we call it initializing. So initializing means we've given it a value. If we don't initialize it, it sort of has no particular value. And it can cause weird issues if we try to use it if it has no particular value to begin with. So I've initialized my integer there as value 42. And because it's a variable, its value doesn't have to change. But when I give it 42, it goes to that piece of memory in my computer and writes the number 42 in there. So it's going to flick the switches, the bits on and off, to the point where it says, okay, this combination of on-off switches means 42. I'm not going to talk in detail about how that's encoded. We might do it a little bit in the tutorials, but we'll see. Because it's a variable, it means it doesn't have to keep that value. I can go back to the thing called answer and change its value. So here I've said, okay, answer now equals 7. I should talk about this equal sign here that I've just sort of snuck in. I've just thrown it in there without explaining exactly what it is. When we're thinking about maths, we think of the equal sign saying two sides of the equals. Everything on either side of the equals is the same. Programming is a little bit different. Programming says whatever's on the left of the equals now becomes whatever's on the right of the equals. So you can nearly think of the equals like an arrow sign pointing to the left. So what we're actually getting, I had to think about that for a second because I'm pointing to my right, but it's your left. Anyway, so what we're actually doing here with this equals is we're taking the value there and we're putting it into the variable on the other side. So we're not actually doing a mathematical thing, which is saying, or are these two things the same? We're making them the same by putting one into the other. We can combine this all together in one go to make it easier for ourselves and say, I'm making a new integer, and while I'm making this new integer, I'm giving it its first value. So we can initialize and declare at the same time. Declare is the creation there. So I've got all in the comments, that kind of thing. We can basically go through and continue using these variables. So this answer, I can continue changing it. I could assign different values to it, and I can even do some complicated maths and then assign values to it and things like that. We also have ways of showing variables to our user. So yesterday, we had the very beginning where we showed hello world to our user by using the printf function. So that was pretty simple, where it was just like printf, and then we just typed in the text in double quotes. When we typed in the text in double quotes, it was going to show it to the user. So, where are we? Back here. Printf. I didn't actually talk about this thing here. You are going to talk about that in your tutes and labs, the /n here. The /n here was like pressing the enter key. So it was like hello world, and then press the enter key, and the kind of the control of the terminal will go down to the next line. We're going to look at that a little bit anyway. Right. When we want to use printf for a variable, we use these little patterns that I have here. So the thing that I'm going to use in this line of code is I'm going to break everything and head back over and point at this one instead. Sorry, 1 second. OK. I'm using this %d. So when I used printf previously, I just had something in quotes, and whatever was in the quotes was the message that I was putting into the terminal. So when I called printf, when it runs, it takes everything in the quotes and just pastes that into the terminal so that the user can see it. Let me just 1 second. Why did that not do anything? Oh, there we go. I'm going to be working a bit in VLab this morning anyway, so I might as well get it started. I'm going to look at the code that we were looking at yesterday. So you can see me working in Linux now. I should probably have done that a bit slower. What I've done here is I've done cd, which is change directory, to go to COMP1511. And you'll see down here, I'm now in my COMP1511 directory. I knew I had a directory in there for lecture 1, so I did cd lecture 1. And then I was in my lecture 1 directory, I did ls to list. And this was the hello world.c in the demo that I did quickly at the end of the lecture yesterday. So if I want to look at the hello world.c file, I'm going to use gedit, which is my text editor that I'm using. I'm going to type in, hello world.c. I'm going to put this and on the end. I think I mentioned this a little bit yesterday. The and on the end means that I'm going to open the text editor, but this window here is going to stay working. If I don't put the and on the end, this window goes kind of dormant. You can't type anything into it, but I want to be able to use both at the same time. So I put the and there, and here's my demo program. So yesterday, when I was working on this, I had a printf for hello world. So what this is going to do, and we can use this printf multiple times for other things. What it does is it grabs the first thing here, which is everything inside these quotes, and it says, I'm going to take everything inside these quotes, and I'm going to write that into the terminal when the program runs. So if I was to run this program again, I'll compile it. Actually, I've probably got it compiled from yesterday, but I'll compile it again just in case. Hello world.c. Actually, you know what I'm going to do? I'm just going to do this so I've got my big path out of the way so that you can actually see what I'm typing in more easily. So when I'm compiling, I compile which program file that I've written. So DCC is the compiler we're using in this course. There are other compilers out there in the world. DCC is one we've specifically written here, which makes it a lot easier to learn programming because it actually tells you a lot of things that are happening in your program that sort of professional compilers don't do. Anyway, so DCC is going to take our code file and turn our code file into a program. So I think everyone will have a decent idea what programs are because you've got them all running on your computers. Basically, if you have any kind of icon on your computer that you double click on, not all of them, the majority of icons you double click on, like, I don't know, like Microsoft Word or like, I don't know, Epic Games Launcher or Fortnite or something, right? I knew that was going to get something. Sometimes I say stuff just to make you laugh. When you double click on something, it's going to take a program and start it running. We can do the same thing here with a terminal where we get a program we've created and we start it running. But what we're crossing over into now is a new world where we don't just double click on programs that other people have written. We are actually going to be making our own programs. So if I'm making my own program here, DCC hello-world.c, that says I'm going to read the file hello-world.c, and then I say I want to output that into something else. So -o is the output, and I think I called it hello demo. You can call it anything you want, really, because this is the program that's going to be written into your directory. Oh, oops. I did the wrong thing. Oh no, I moved my directory. I did CD to the tilde. Okay, so where I am now is my home directory. I've got to go back to my COMP1511, and I'll do a listing in here, and I've got lecture 01 that I'm going to. I'll do a listing in here, and I've got my hello world here. Show you a cool trick. This is something that you will probably use a fair bit when you're retesting and testing code. If I use the up and down arrows, I can go through my previous commands. So I can actually find my old DCC command there and then run that again. So this should work this time because I'm actually in the correct directory where my files are. Okay. One thing about working in a terminal in Linux is if you don't hear anything, it means it's done something. I know it's weird, right? Because usually we'd get like a confirmation in other operating systems saying this thing has completed. All it does is just goes, yeah, done. It'll tell you something goes wrong, but usually if something goes right, it just won't tell you anything. It'll just be like, okay, good. So now I've got hello demo, and if I want to actually run that program, I use this particular symbol, which is /. // is going to say I'm about to run a program that's here in this folder that I'm in right now. And then I'll type in the name of the program itself, hello demo, and I'll run that, and it does hello world here, plus this little weird thing here, which is the new line symbol, which means that my prompt then goes back down to the bottom of the line. I'll show you what happens if I don't do that /n. So the /n is like pressing the enter key. I get rid of that. Save this. You've got to save it before you compile because it's going to compile the file that's on your computer. One of the most common things that we do all the time is we forget to save it, and then we compile it and run it, and nothing changes. So I just press Control-S here to save this file, and I'm pressing up twice to get my DCC command, which is going to compile that file again. And then I'm just going to press up again until I have my command that runs it. So this is how we do this a lot. We just press up and we find our old commands, and it makes it easier to redo things. Run that, and it does a lot of the same thing. It does hello world, but instead of having my terminal down on the next line, it's right on the same line as the hello world now because I didn't get the hello world to press the enter key basically at the end of its printout there. So I'm going to put that /n back in here. Oops. I accidentally got rid of the entire rest of that line. Okay, so if I compile that and then run it again, then we go back to the way it was with the enter key. I just sort of wanted to show you that because that's something I didn't show you at the end the other day. Okay, so if we're going to print variables now, the same kind of thing happens where everything that's inside the quotes, I've got to remember not to walk all the way over there, everything that's in the quotes is the stuff that's going to get printed out. But if we want to print out things like our variables, we're going to need to sort of deliver those variables to that thing in the quotes and say, this is what I want to print out, and this is where in the quotes I want it to be. So this example says, this %d is a symbol, and it says, this is where I want this number to be. So %d specifically says, I am going to print out a decimal integer, and our integers are decimal integers. If you've heard of different kinds of numbering systems, there are like hexadecimal numbering systems, there's binary numbering systems. We use a decimal numbering system most of the time. I'm pretty sure based on the fact that we started out as people counting on 10 fingers, which is why we say that 10 is the point where we add up to another digit. I don't really know the historical details of that, but I'm pretty sure that's why it is. So the %d says, I'm going to put a number in base 10 here in this string of letters that I'm going to print out to the terminal. That's where I'm going to put that number. And then we put a comma there, and after that we say, okay, this is the actual variable that we want to put in where that %d is. So when we print this out, if I've had the number and I've declared it and initialized it as 7, this is going to print out my number as 7. I wonder if actually, as far as I remember, I actually have code for this. I'm not going to bother writing it now because we're going to do other code later today, but there is example code for all of this, so you can grab it and run it if you want. Or you can look at it in the tutorials next week because there's going to be lots of stuff in the tutorials about it. If we're going to print more than one variable at a time, it matches them up in order. So if I have 2 numbers there, and then I have 2% symbols, %d symbols in this printf, then I'm going to need 2 variables afterwards, and we just separate them by commas there, and we say print this one, then print this one. I should point out a little bit of the basics as well. There's a lot of like little grammar about how we do instructions when we're writing code, is that pretty much every line that's a complete single instruction is going to end with this semicolon. The only lines that don't end with a semicolon are things where we're opening and closing brackets. So every time we have a single instruction which just tells the computer, just do this thing, we'll put a semicolon on the end to say to the computer, I've finished with this instruction that I'm telling you. You'll get a hang of this as you go along. You start to get natural with the semicolons. Unless you've done Python, in which case this like kind of like twists your head around because they don't use semicolons in that language. We can print more than one type of variable. So that %d is not the only way that we can print something. The %d was there for a decimal integer. We also have another symbol called %lf. I'm going to apologize in advance, and this is probably not the only time I'm going to apologize about this. There's a whole bunch of stuff in C and Linux and things that, I mean, C was, if I remember correctly, first created in the late 70s and has been iterated on bits and pieces, etc. since then. So there's a lot of stuff in it that's sort of from legacy computing. So instead of that %lf being, I want to write a double here, it's this weird way of encoding things where it's like LF stands for long floating point number, which is the 64-bit floating point number, which is our double. So we call it a double, but the symbol to actually print it out with a printf is LF. There are a few little weird things like that that are always going to happen when we're programming in C. I apologize that they don't always kind of make intuitive sense, and they're the kinds of things you have to memorize. You will probably get a handle on these things the more that you code, but for the moment, these are things you're going to have to remember. If you want to print out an integer, it has to be %d. If you want to print out a double, it has to be %lf. So a little bit weird, but we will kind of get the hang of these things as we go along. So here I have an integer and a double, and I can print out an integer with a %d. So I put the %d in there, and so the first symbol in this string of letters is the first variable that I put here afterwards, separated by commas. So The first one was the int, and so I put the diameter in there, which is an int. And the second one is the double, and I put the double pi afterwards there. So this kind of format, you get a bit of practice with this, you'll be able to print out lots of different things, lots of different numbers. The trick is, where you want the thing to print out is where you put the %d, and then you match it up with the variables after the commas afterwards. We can also put information into our variables from what our user tells us. So the user can actually type stuff in the terminal while the program is running. We can actually make space for the user to type things in. And we will scan in that input using a function called Scanf. Scanf is very similar to Printf in that it has the same kind of quotes and it has the same kind of symbols. The difference, however, is it is not grabbing the value of a variable. It is actually being given the location of a variable and saying, when the user types this in, go to that piece of memory that we reserved for that variable and write over it with whatever the user typed in. So this AND symbol in the scanf is something we're going to talk about a lot later. But for now, you can just know that this is something that sort of helps us know where the variable is. Later on, we're actually going to be delving deep into this, but I'm not going to go too deep into it right now. Oh, question?
Yeah. Why do we need to specify what kind of number it is? Why can't we just say, for example, %n? It's a number.
So the question was, why do we need to specify exactly what kind of number we're using? Like, why are we using %d and %lf and things? Why aren't we just saying, it's a number of some kind, please just sort of deal with it? The reason we're doing that is because C is very specific about these things. So let me guess, have you done some JavaScript before? No? Oh, you haven't done other programming? Other programming languages have this idea that like a variable is just a variable, which means it can be anything. And how we treat it is just how it ends up being used. So we could have a number and it could be treated as a word or a number. But in C, C is very specific. So C wants everything to have its exact purpose only. And anytime someone tries to use something that's not for the purpose it's supposed to be, it will say, no, you can't do that. So it's nearly like a safety measure. So if someone accidentally writes the wrong code to read an integer as if it was a double, or vice versa, then C is going to be like, okay, there's something going weird here. And it will let you know that there's an issue. So there's a sort of constant back and forth between programming languages themselves, that some of them are what we call strongly typed languages, so every variable has to have its specific use, and other languages where they don't have to have their specific use. You can join this argument later on in your degree. It's kind of like whatever, like Mac versus PC as an argument, or like PlayStation versus Xbox, that like they're all useful in their different ways, but people like to grab a camp and then argue against the other ones just for the fun of it. Okay, so back to reading in, sorry, is that enough of an answer of the question? Yeah, cool. So reading in these variables, we use the same kinds of symbols, but we're now using a different function called scanf. And this is also something that came from the standard input-output library. So we have printf and scanf here, and then scanf says, I can take in a certain type of thing that the user has typed in. So here with %d, I'm expecting a whole number, an integer. And this is where I want it to go. So I want it to be put into the variable input. So I say, input's the variable I'm going to go into, but I need to give this and to say this is where this variable is. So there's details in that we're going to go into later, but for the moment, just understand that scanf is going to use the and in front of the variable name. Do we have a question over there? It looked like you were about to ask a question. Yeah.
So therefore, when you're doing the scan, as you're making the integer, it actually doesn't put a value until the user types it in.
Yeah. Let me ask it in for everyone so they can hear it. So the question was about, let me make sure I get that right. When we do the scanf, the integer didn't have a value before we did it, except it had been declared, so it had the bits, the 32 bits in there, and then when we did the scanf, it was going to write into those 32 bits. So yes, when we do the scanf, it's going to find those 32 bits, and it's going to write whatever the user just typed in into those 32 bits. The interesting thing about it is it doesn't matter whether that input integer there had a value beforehand or not. So if we wanted to, it could have had a value, and then we could write over it. Or it could not have a value, and we could still write over it. Because scanf, no matter what happens, it's going to write into those 32 bits. Usually, we would probably have a value here first, because it's a bit dangerous to have an integer floating around with no value. Because if we start trying to do calculations to something with no value, then things just go a bit weird. Okay, so we can read in an integer or a double using those symbols that we saw before, the %d and the %lf. There is another type of variable that we can use. Well, it's not actually a variable. Oh, before I go on, question? Yeah. That's a good question, and it does come up a bit. What I suggest is take that bit of code, write it in, and then try it. So it gets weird. So when a user types in something that isn't what we expected, so it isn't the type we expected, then C gets a little bit weird about it. Most of the time what it does is it will just straight out ignore the thing that was typed in that was the wrong kind of pattern, and then it will wait for the particular type of number to come in correctly. So usually what it'll do is it'll just throw away everything that it doesn't like. Another question? Yeah. The question was, what if we need to work with both words and numbers? We're going to talk about the words later. So for the moment, we're going to build up a vocabulary of working with variables using just the numbers, but we will definitely be doing letters and words later, because it's pretty hard to work without the letters and words, especially if you're working with humans. And most of our programs are going to work with humans. Another question there. The question was, if I gave an integer a value of 0, is that the same as not giving it a value? It's actually different. So not giving an integer a value like this one here is not necessarily going to give it a 0. I say not necessarily because some compilers, when they translate the code, will give it a 0 on the assumption that you didn't give it a value, but you probably wanted this to still be workable as a number. Other compilers will be like, if you try to use this without giving it a value, they will just throw up a massive alarm and going, this has no value. I don't know what you're trying to do with this. Some other compilers, I think DCC won't necessarily do that, but I think it will leave the integer with a magic number. So there's a magic number that you might see whenever you use, again, okay, this is going to be my answer to nearly all questions, is do it and see what happens. So make an integer, don't give it a value, ask it to print out. I'm pretty sure, if I remember correctly, it's like -5 million something. There's actually a magic number in the range of integers, which is the magic you didn't initialize this number. However, it's still a value you could use in the integer. So it's a bit weird. Another question over there?
How does Scanf behave with hostage trading code that costs?
Say again, sorry? Oh, the question is, if we are using scanf here, and this double quotes means a string of letters, but what we're saying here is this symbol says decimal integer. So I think this is similar to the question over there, what happens if we type in something different, is that this is going to expect the user at this point to type in something that matches an integer, so a whole number. And I think usually what it will do is we'll just sit there and wait until it reads a whole number, and it'll throw away anything else the user types in until it gets there. But to be sure, I think it's a good idea to write, even just copy-paste this little bit of code inside the int main, inside the curly brackets, and then run it a few times, play around with it, and see what you get. Because you'll get some interesting results out of typing in different things. There's more to scanf as well that we can look into later, but for the moment, we're just going to kind of assume that people are giving us the correct information until we've learnt more about how to deal with things when we don't get the correct information. Okay, so that's reading in, oh yeah, constants. Sometimes we have numbers that are not going to change. So we can't call these things variables because they're not going to change. They're going to be things that remain the same for the entire use of our program. And we call these constants, and they actually happen outside of the program themselves. They are not instructions that the program is going to perform bit by bit, so we're not going to declare variables. We're not actually going to assign memory to these things. They're just going to be pure values that become part of our program itself. So one of the most common ones we're going to get from this is something like pi. If you're doing anything with circles or rotations and things, you're probably going to need a value for pi. C doesn't have a default value of pi, so we tend to just throw it in whenever we need it. These commands happen up above the main in amongst things like our includes, which is why they have a hash in front of them. So the hash define is going to say, I'm going to give you a symbol, series of letters, and then after that I'm going to give you something else. And then everywhere in our code where we see this symbol, like the pi here, it's going to replace it with this number. So it's not a variable. It doesn't have a place in memory. It doesn't have a certain number of bits it uses. It can't be changed either, but it's something that our computer just sort of remembers and that we can keep using through the course of the program. Have a question there? The question is this just a text replacement? Technically, yeah, that's exactly what it is. So what it will do is before it looks at all of your code, it'll go through and find everywhere that says pi like that and just replace it with the second symbol. So it doesn't have to be a number. There's other things that we can do with hash defines. We can hash define words and things like that. But this is a way for us to say that for the entire running of the program, this symbol here is going to mean this symbol. So I can save something like pi or other constants. Yeah? Oh, the question was, if I was then to create something which is like int x equals capital Pi, well, if you name your variable xpi, let me just see. Let me just type this in and see if I get what you mean by this. So if I have made one called pi 4159. That's about as much as I remember. I bet someone in here knows more digits of pi than me, but let's... Okay, and so what you're asking is, if I make an integer called xpi like this, because it's all one word like this, is just going to be as it is. So this integer is called xpi. It's not going to do the exact text replacement here. But if I do this, that is going to work. So at this point, I'm going to get that 3.14159. I'm not even sure if that 2 is correct or not. I think it is. It's like 24 or something. I know I just read it a second ago, but I still can't remember it that well. That there is going to take the value that I've got up there in my define, and it's going to put that into that integer. So I can use those numbers in my code. Question over there. Constants do not have types. Sorry, the question was, do constants have types? They don't have types. So you can do all kinds of things in constants. Okay, where was I? I can't remember how many more slides I was going to do before the break. Oh, not much. Okay, cool. We can also do maths in code. So we have symbols, some of which you're going to be very familiar with, which do exactly what you think they're going to do. A plus, a minus. The star there is going to be our multiplication. We're not going to use an x for multiplication because x is a letter, and x can be used as a variable name and other things like that. So we use a star. The slash is going to be our divide. So when we put these in between any two numbers, they're going to do what you think they're going to do. They're just going to basically do the maths on those numbers. So if I do 1 plus 2, I'm going to get that whole thing meaning 3, basically. But the cool thing that we can then do with this is we can start using variables. So if the variable has a value, like here, x is equal to 5, y is equal to 10, I can say 5 plus 10 multiplied by 5. That's going to be 65, I think. I don't do very much maths in my head, frankly, because the more time you spend with computers, the more you get them to do it for you. But, you know, this is going to do that maths. And like I said before with the equals, it is not going to say that both sides of this should be the same. What it's going to do is it's going to say whatever was on the right gets assigned to whatever's on the left. So what it's going to do is go through here and do all of this maths with the brackets. The brackets can do precedence. This is like I hope everyone here can do this level of maths, because this is like, I think we're in year 6 still here, right? So we do this maths, and all of this is going to come out to a single number. And for the moment, this is going to be a whole number, and that whole number can be put into an integer here as a result. So whatever this comes out to be will be assigned to the memory that result holds. It'll write into that memory, and then the result variable will have that value, which we can then print out. So this kind of thing is just like the most basic operations with maths. We're going to be doing more stuff like this. And obviously things are going to get more complicated as we go along. There is only one weird thing about the maths. The weird thing about the maths is divisions. So I'm going to talk first about actually the second point there. Oh, I'll talk about both of them, right? So the first point is any mathematical operators that involve certain variable types will output the same variable types that went in. So if you have any doubles, this is mostly for divisions, because I think it's impossible to multiply two whole numbers and get something that's not a whole number, right? Because to multiply something to get a not a whole number, it has to be a fraction. So usually this is going to happen only with divisions. If there's a double in the division anywhere, then your output's going to be a double. So if there is a floating point number, if there's a fractional decimal number, not decimal, a fractional number, a real number, anywhere in the division, the output will also be the type double. If there's only integers in a division, the output will be an integer. The weirdest thing about integers is they take fractions and decimal, oh sorry, I keep saying decimals, but decimal means base 10. Anything with a floating point or a fraction or anything, the integer is simply going to throw it away. So integers, when you divide them together, they don't care about any fractions, they throw them away. So they don't even round them off. So you don't even get a nice thing where it rounds it. It actually just says, I store whole numbers only, and the result of this division is a whole number and a decimal and some other stuff. It just grabs everything beyond there and says, I don't care. It only takes the digits that make up a whole number. So I've got some examples here, or at least one example. If you do 3 divided by 2 and they're both integers, you don't get 1.5. So 3 divided by 2 normally, you would expect that to be 1.5. We're not getting that with integers because the integer says, I don't do fractions. So it says, if it was going to be 1.5, then I'm going to take the 1, I'm going to throw away the half. So integers are only going to store whole numbers. 5 over 3 also will result in 1. So integers are always going to, if you do a division, they're going to throw stuff away. However, if you want to know the remainder of a division, we do have another thing that we can do for that, which is called modulus. And that's this weird percent symbol. We're not going to be using the percent symbol for actual percent. It's used for this particular command. So the 5 divided by 3 was going to be 1. So this is like going back to, I think, primary school maths. If I do 5 divided by 3 in the old primary school way, it would be 5 divided by 3. 3 goes into 5 once with a remainder of 2. So we've got 3 going in once with a remainder of 2. So the division with integers will result in 1, saying that 3 only goes into 5 once, and it won't care about the remainder. But if we do want to know the remainder in this situation, we can use this percent symbol, which is called modulus. We call it mod for short. 5 mod 3 gives us a 2, which says that I actually don't care about the other end of it. I don't care about the division. I don't care how many times 3 went into 5, but this is the remainder that comes out afterwards. So knowing the remainder from a division can give us some useful information, because we can tell what numbers something's divisible by what kind of remainder we get out of things. We're going to show that later today as well. So 5 mod 3 results in 2. saying that the 3 went into the 5 once, but we didn't really care about that. We cared about how much was left over, which is the 2. So the division and the mod give us the capability to do some different things with numbers. I'm going to show you an example later today that gives you more information about this. Okay, so let's take a 5-minute break. And I've got some information here thinking about what a program is. It's a series of instructions that are going to be executed in order. Some are going to be do this thing, others are going to be store this information, and they will nearly always be top to bottom. So we do have a message, I think, in the break today. So we'll listen to that, and then we will come back and do more programming. Yeah, do you want? Let me just switch over to the other one.
And thanks again for...
Yeah, no worries. Okay, here's your mic. You might want to hold this bit as well. It's a bit heavy. Yeah, it's not.
Hello, everyone. PC Sock will be hosting a LAN party this weekend right here on campus at Colombo Building.
You might have to hold it up to your mouth. I don't think they'll be able to hear you. Yeah. It's a bit loud in here. Okay.
Hello, everyone. PC Sock will be holding a LAN party this weekend right here on campus at Colombo Building. We have tournaments and prizes with plenty of giveaways to be won by everyone. So if you consider yourself a pro gamer, then come on down to Colombo Building. Or even if you don't even own a PC at all, still come down anyways, because we have like free play laptops available for everyone to use. Free of charge, by the way. The entire event is free of charge. And you don't even need to join our society. There's literally no commitments. Just come on down, play games with your friends. What better way to start the year, right? For anyone interested in trying out virtual reality, we also have 2 headsets available for free play, including a selection of games such as Beat Saber, Pavlov, Superhot VR, and Robo Recall. And joining us this time around, we also have Minecraft Sock, UNSW Esports, and Smash Sock, who will be holding their own tournaments. For more information, visit bit.ly/hyperlan. I repeat, bit.ly/hyperlan. So once again, LAN party this weekend, Colombo Building. Come on down, I'll see you there.
Thanks. I think that should be fun. I reckon you got a lot of gamers in here.
Yeah, me too, I think so.
No worries.
Lots of gamers in CSE.
They usually don't go quiet for the presentations. All right.
Thanks again.
No worries. See you soon. Yeah. All right, let's get back to it. Am I? Yes. Oops. Okay, I'm going to jump straight back into it. I showed you some Linux stuff yesterday, and I'm going to show you a little bit more of it now. If you want to play around with these things, it's pretty easy to, especially if you're connected to VLab. Actually, hands up here who is already able to connect to VLab and has tried it so far. Good. Okay, so we've got heaps of people who can do that. And if not, you can check it out soon, or you can go into the actual CSE computer labs at a time when someone else isn't teaching in there. You can use those computers anytime you want. Those are good times to actually try out these little commands. So I've got some new ones here for you to play around with if you want to. So in a normal operating, well, normal, Linux is also a normal operating system. But in the operating systems you might be used to, we're used to moving things around with like mouse and keyboard and stuff like that, copy pasting things, deleting things and stuff. In Linux, when we're working in a terminal, we're going to be doing the same things, but with all text commands. So I can copy files, I can move files, and I can delete files and things like that. Let me go back in here. Let's see what I've got in my lecture 2 directory. Okay, so I'm going to change directory. Let me show you one thing that you can do with changing directory. So if I want to go back a directory, so I want to go up a directory to my COMP1511 directory, I do cd dot dot. Dot dot's going to go up a level. So I'm now back in my COMP1511 directory. I can do ls to look in the directory, and I can see I've created a lecture 2 directory previously. I created that using the mkdir make directory command. But if I want to just move into it, change directory to lecture 02. Now I'm in the lecture 02 directory. I can have a look at what's in there. So I've got a print demo in there. I think this is the same thing that's available with the slides. I can open that, have a look at it. But if I want to do things like manipulate this file, so here I have the ability to copy a file. So I can copy from one file to another file. I can do something like cp copy print demo.c. Let me show you another trick. So say I've got a bunch of files in there, and I know that some of them are named a certain way and some of them are named a different way. If I do something like just PR, because I know that there's a print demo in there, and I press tab, tab will auto-complete things like file names and stuff. So you can actually get really, really fast in the Linux terminal if you learn things like the up and down arrows and tab for auto-complete and stuff like that. And then you end up sort of flying through these things and being able to navigate things really quickly. I know people out there who are like, who don't like the mouse and keyboard way of working with, like they don't like mouse GUIs because they think the mouse GUIs are slower because they've gotten so fast at typing things. So there's ways to get really like super fast with this kind of thing. So if I want to copy, I can copy print demo, and I can make a copy of it called, say, print demo 2. I don't know why I would necessarily do this, but maybe I wanted 2 copies of this program so I could fiddle with one while I keep the other. So I do that, and in that hilarious Linux way, it doesn't tell me that it's done anything. It just goes, yeah, cool. But if I do a listing here now, you can see the 2 files are there. So I've copied one file and made it into another file. Okay. We can also move files. So I can move files into another directory. So if I wanted to, I can say move print demo 2. I'll tab. There you go. It completes as much as it can. Move print demo 2 to another directory. So I'll just do dot dot / I'm going to put in my lecture 1 directory, which I don't really want it to stay there. Tab complete. handy. I do this, and it's going to say, move this file into this location. Classic Linux doesn't tell me what it's done, but it has done it. So if I want to go see whether this worked, I can go cd ... to go upper level, cd lecture 01, ls to look in here, and I can see my printdemo2.c is here. So the mv command was able to move the file around. I can also do weird things with the mv command. I can move it to the same place it is now, but with a different name. So I can actually use the move command to rename files. So if I take print demo, I'm going to tab complete that, so it's nice and easy. I don't have to type the whole thing in. So I'm going to move print demo into I don't want this here .c, because it's a program from lecture 2. I don't want it in my lecture 1 directory. I'm just going to rename it that for fun. I don't want this here. Do my ls again, and my file now has changed to I don't want this here. So we can use the movement command to actually move a file to a different name without actually moving its location. The other thing is, well, I know now I don't want this here, so what if I want to delete this file? If I want to delete this file, we don't actually say delete, but we say remove, which is rm. So I can do rm on I don't want to type this in again, so I'm going to press tab, and it's going to autocomplete. The tab autocomplete is going to do the best job that it can. So if you have a whole bunch of files that start with the same letters, it's probably not going to know the difference between them. But because there was only one file in here with an I, then it autocompleted. But either way, it's usually going to speed things up. So I'm going to remove I don't want this here. And then if I do ls again, I don't want this here is gone. As with all things, just be careful of that. So don't do rm assignment1.c 5 minutes before you're going to submit it. I mean, we have backups of things like that. We're going to show you ways to back things up, but just be careful with it. The other thing that we can do is we can do a -r. -r stands for recursive, and what that's going to do is we can do that on a folder with a -r on a directory. Sorry, I go back and forth between folders and directories because everyone calls them that anyway. Recursive means it's going to go into the folder and it's going to grab everything inside the folder and it's going to do that command to everything inside the folder. So if we do cp-r to a folder, we'll copy the folder and the new folder will have all of the same contents as the previous folder. Be very, very careful of rm-r. So rm-r is going to go into a folder and it's going to remove all of the files inside the folder. So if I was to say go, for example, COMP1511, rm-r, my COMP1511 directory, then you have no coding examples ever again. So obviously I'm not going to do that, but I have backups from the last few times I've taught this, so it'll probably be okay, but just be careful of it. So the -r is useful, and it's really useful if you want to copy a whole directory. It is also good if you want to remove an entire directory, but again, just, you know, double check what that directory is before you go removing stuff from it. Okay, those are a few Linux commands. They'll come in handy here and there. Okay, next thing I wanted to talk about is letting our computers make their own decisions. So up until this point, every program like that I've shown you, all of those little code snippets, they're always just going to do the same thing. No matter what the situation is, they will always do the same thing. They were always going to print something out, and the number they were going to print out was always going to be the same. Scanf may be a little bit different, because they were going to read in whatever the user typed in. But what we want to do, and this is like getting into actual programming in a sense, this is the stuff that makes programs more intelligent than just simple tools, is the ability to make decisions based on the information they get at the time. So in C, this is known as the if statement. Anyone who's done any other program has probably seen this in other programming languages as well. The if statement allows us to turn on and off sections of code that are in our program. So we can say, if a question that we ask is answered in the right way, then we will run a certain section of code. Otherwise, we will not run that section of code. We might do something else. So the if statement looks like this. I like to think of it as a question and an answer. So this format is always going to be the same. The keyword if, this is a new keyword for you. It's the same as keywords like return or int or double. You can't use it as a variable name. C is going to be very specific and say, if you type in the word if, I know that that means something, and I'm going to start using it as if it means something. So if will be followed by a normal set of brackets. In those normal set of brackets is a question. I'm going to leave it like that for now. I'm going to show you what the question is in a second. But this is the format. It's got a question. And then inside these curly brackets is an answer. So you've seen these curly brackets before now when I showed you the main from the hello world. And basically everything else where we've had a set of instructions is going to be inside a set of curly brackets. So we've got the curly brackets, and then inside there we've got some code statements. So those code statements can be stuff like a printf. It can be some maths assigning variables. You can be declaring variables. So I've shown you a couple of those things already that can go in there. If the expression that's in there is answered in a way that we like, then we're going to run these statements. If it is not answered in a way that we like, we're going to skip over everything that's in these curly brackets and not run it. So now we have the option to run or not run bits of code. We also have else statements. And so the else statement follows on directly after the if. So we've got an if, a question, and then an else. So if the question comes out the way we want it, and now I've got the details of exactly how this works. All of your variables so far are numbers. When we're considering numbers in terms of true and false, we're going to be asking these questions as true or false. So the expression there is either going to be true if it's any value that's not 0, or false if it's 0. Most of the time when we're working with these, we're just going to say true is 1 and false is 0. But we're actually going to be working with these that any number other than 0 is going to cause that expression to be true. And then a number 0 would make that expression false. The structure with the if and the else is that if the expression there turns out to be true, and we'll talk about how we can ask questions in a second, then the bit in the top runs, the curly brackets at the top run. If that expression had been false, the bit at the top will not run, but it will skip down to the end of that and it will see the else, and the else will say, the if was false, now we're going to run this code instead. So we can make an explicit decision between two pieces of code. Because of the way the if and the else works, only one of these can possibly run. Because that expression there gets tested once, and it either gets called true or false, i.e. non-zero or 0, and then it picks between these two bits of code for what it's going to run. We're going to be using a lot of this, because a lot of the time our code's going to say, look at a variable or look at something, and then based on what we're getting out of it, then we're going to choose what we want to do. We can chain these as well. So we can do an if, and we can do an else if, and we can do an else. We can actually kind of do these forever. Ifs and else ifs and else ifs and things like that. Should point out something interesting as well, and this is something that's going to come up again and again and again. The if statement is a piece of a program. So when I said before here code statement, I was being intentionally really vague here in that any code statement can go inside an if, which means an if can go inside an if. And then another if can go inside that if. And then you can get this big, big, deep chain of all of these questions where all of them have to be answered correctly before a piece of code will run. The risk that you're going to get if you chain too many of these things together is the one thing that I was talking about that, like say 50% of the code we write is going to be for humans. The deeper you go into this, if this, and 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 then your human reading that is like, I don't know where we are anymore. I can't keep track of that many questions at once. So the thing about building these up is if we put too many inside each other, then people aren't going to understand it anymore. But with this if-else, we're getting, if expression 1 is true, this runs. But if expression 1 wasn't true, then this one runs, but it only runs if expression 2 is true. Otherwise, this will run, and this will run if both of the others were false. So you get this kind of thing. You know those riddles of like, this person always tells the truth, and this person always lies. So you walk up to this magic door, and then one of them says, one of us always tells the truth, and one of us always lies. And the other door is like, look, it was just one time, all right, can you just get over it? So, it's a recent meme, it's okay, fine. Yeah, anyway. So if and else allows us to take this actually potentially complex path through decision making to decide exactly which bit of code we're going to run. Now we need to know what questions we're going to ask. So that expression that's inside the if statement is a question that's going to result in a 0 or some other value. And so to figure out whether we're going to get a 0 or another value, we need to have a set of questions that we can ask. At the moment, the only variables I've given you are integers, and so we can work with integers and we can ask questions about integers. So this is a set of what we call relational operators. And some of these are going to be really obvious because you've done some simple maths before. So greater than and less than. We can put variables on either side of that, or we can put values on either side of that. We can say, is this variable higher than the number 10 or something? And then we will get a result out of that. So we can use the combinations of variables, constants, and just numbers that we type in our code to ask these questions. We can greater than or equal to, less than or equal to. We also have this equals. So, before I was trying to make it really clear that a single equals is not a mathematical equals in programming. I wish that we could go back and change the way that C was written so that we never used the single equals to put values into variables, because then we could use the single equals here and the maths would actually read correctly. But the way that we're going to have to try to remember this is a single equals is an operation where we put a value into a variable. The double equals is a question. So the double equals is saying, are these two values equal to each other? And then we have a not equals, which is the exclamation mark and an equals. And all of these are going to result in a 0 if it doesn't make sense mathematically, or a 1 if it does make sense mathematically. So now we have questions we can put in the if statements. The other cool thing we can do, and this is probably new to most people, unless people are doing discrete maths at the moment, we don't do that much logic, I think, in high schools. We can ask questions about the questions. So we can say, let's have two questions next to each other, and we can say, how do we combine those two questions into getting some information out of them? So the two things that we're going to look at here is and or. Is anyone here doing electrical engineering? Oh, no, wait. Oh, wait, we do. We do have a few. Okay. Because I think everyone in this room has to be doing a computing program of some kind to be in this class. But I think there's going to be people doing combined electrical and comp sci, I think. Any of those people? Something like that. Yeah. So there's at least one up the back, yeah. So those of you doing electrical, you'll see a lot of this because these are gates. So they're gates where 2 bits of voltage go in and then 1 bit of voltage comes out. This is the same kind of thing, where we'll look at expressions on either side of these things, and the or says, I'll do the and first because it's higher on my list. If both sides were true, then the and is true. So this and this, then it will equate to true or false, so 1 or 0. The or says if either of these, so you kind of think about it in English, it sort of makes sense, right? And is both of them, or is either one of them is fine. So the or will be true if either side of them was a 1 or anything other than 0. The and will be a 1 if either side is greater than 0. We can also use not, and not takes any expression and just flips it. So I can have something that's true and put a not in front of it and it will become false. Let me show you some examples so you get an idea of how this works. So first one's simple. 5 is less than 10, and the result of that is going to be 1. So if I put that into my code, 5 less than 10, if I put that into an if statement, what's in the curly brackets will always run, because 5 is less than 10 is always going to be true. We're just going to assume that. I'm not going to go into quantum mechanics and the theory of numbers and I don't know. I think aliens would have to be involved before 5 is not less than 10. Someone would have to teach us another way of using maths. 8 is not equal to 8. That's obviously false, so that's going to equate to false. 12 is less than or equal to 12. 12 is less than or equal to 12 because they're equal, so that's going to be true. And then we start combining these things together. So I've got an AND statement here in between two relational operators. So I'm saying 7 is less than 15 and 8 is greater than or equal to 15. The total of that is false because 7 is less than 15 is true, 8 is greater than or equal to 15 is false, but because I said and, I needed both sides to be true before this was true, so that is false. However, if I ask exactly the same questions, but with an or in between them, I only needed one of them to be true, and then the whole thing is true. There. And then we've got a really complicated one here, which has an or of two of them. 5 is less than 10, 6 is greater than 13. So 6 is greater than 13 is false. 5 is less than 10 is true, which means the or there is true because one of them was true. But then we put a brackets around the whole thing and put a not in front of it, which flips it. So the whole thing was true, but then we flipped it and it became false. These are the kinds of questions you can put inside an if statement to decide whether or not you're going to run code. But the key element that's going to make these much more interesting is that these numbers don't have to be these numbers. They can all be variables. So you can test where your code is up to at a particular point in time and going, are our numbers above a certain point? Are they below a certain point? Do they equate in this really weird way to things? Is one of these two cases happening at the moment? I didn't put an even more complex thing in there where I could take this entire thing at the bottom here, put an and next to it, and attach it to one of these others. You can just keep going. Again, no real limitations to what C can handle in terms of how complex you build up your maths. But there is a massive limitation for what you or other programmers can handle when you're trying to read it. So just be careful, because the more bamboozling you do to yourself to other programmers, the less likely you're going to have code that you actually understand or know that it definitely works. Question over there. Oh, right. The question is about order of precedence. This is the general mathematics thing. Which things go first? So if you know about maths, you know the brackets always go first, and then the multiplies and divides go next, and the additions go later. You do have a similar order of precedence here in that the little relational operators between the two numbers, they will go first, and then the logical operators that chain the questions together will go after those have been resolved. Yeah. But brackets first as well.
But like within the logical operators.
Yeah. The logical operators, I think that not goes first, and then and or go together. I think. You may have to look that one up. I have so many things that I just sort of use, and I forget the exact details on them. Okay, so we've got some time left. We are going to now create a program. So in order to not get sued, this program is for use in a game called Catacombs and Large Reptiles. It's not really. I'm not going to get sued by saying D&D. Who plays D&D here? Okay, we've got a few. Okay, good. I should put my hand up as well. I don't specifically play D&D, but like other RPGs and stuff. All right, well, that got a lot of people talking. That's cool. So this example is going to be used in some kind of game. It's not exactly D&D, but I mean, it could be. The way I'm going to describe this is I'm going to describe specifically what's going on, and then we're going to put it together into a program that meets this. This is the way I'm going to be doing most of the examples that we're going to be doing in class. So a user is going to roll 2 dice. Anyone got dice on them? I don't have dice with me right now. I have some in my office. But anyway, the user is going to roll 2 dice, and the user is going to tell us the values of those 2 dice. You can already think about what kind of code I'm going to write to do that. So this is why this example is really to set this out. The program is going to add together the values of the 2 dice that the user has rolled, and then it's going to check that against a target number, something that the program knows that the user doesn't, and then it's going to tell the user whether the dice total was higher, equal, or lower than the secret. We're not going to do equal, by the way. We don't need to do that right now. I've actually set that as a challenge instead. So we're just going to figure out whether the user adding the 2 dice together was higher or lower than our secret number. You can kind of tell already if you think about this. There's a lot of things in here that are going to use exactly a lot of the code that we have talked about today and a little bit yesterday. So what do we need? We think about how we're going to piece together the bits of code that we've thought about today, and how do we actually piece that together into a program. So we need to be able to talk to the user. We need to be able to tell the user what's going on, but we also need to get information from the user. So we know that we're going to need to use Printf and Scanf. We're going to need to tell them something. We need to receive something back. We need a way to compare numbers, because we've said we're going to add two numbers together and we're going to compare them against some secret number, which means we're going to need our relational operators. And given that we're going to use these greater thans, less thans, and stuff like that, it means we're probably going to put these inside if statements and do something with them. We're going to test these against a secret number, which means there's a number in our code somewhere. Secret number can be a constant or it can be a variable. I will probably use a constant for this just so I can show you different ways of doing things. We also need to be able to run different code depending on the comparisons. So depending on the numbers we're comparing against, we're going to run one piece of code if the roll was a success and a different piece of code if the roll was a failure, right? So we're going to use our if statements to split up which code we're going to run. So this should chain together everything that I've talked about today. So first thing that we're going to do, and this thing that makes it kind of easier to work with, is we're going to describe our program. I'm probably going to hop out of the slides now and just go straight into VLab and some coding. So let's go. ... takes me back to COMP1511 and a slash, and then I can go to lecture 02. So I'm now in my lecture 02 directory. I'm going to start a new file here. I can start a new file by opening my gedit program and saying the name of the file that I want to make. So I'm going to call this dicechecker.c. The .c just signifies that a file is a C program. So pretty much everything, not everything, but pretty much everything that you're going to write in this course is going to be a .c file. Did I spell that incorrectly? I did. Okay. Dicechecker.c, it opens my gedit and it gives me a blank file. So the blank file means I need to set this up properly. First thing I'm going to do, is I'm going to put some information here for humans so that they don't have to read through all my code to figure out what's going on here. They can just read the first line and go, okay, this is that dice checker thing. What are we? February. Oops. Is anyone else still doing that as well? I will often just put the month because I know that I'm going to be working on a piece of code for a while. Although this one I could probably just put today because I'm going to hopefully finish this today. Anyway, I would usually put more information. As you can see in the lecture slides, I put heaps of information there that says exactly how the program runs. But in the interests of getting this done so you can see the code, I'm going to do it quickly. Some of the things that we're going to have in pretty much every program we're writing is we're going to have this include standard input output .h. Again, we're going to go into what that is specifically later, but for now, just understand that this line allows us to use Printf and Scanf. Then the thing that starts our program, int main void curly brackets. I have a habit, which I think you should probably get into, is every time I open brackets, I close them immediately. So we open the brackets and we close them so we know, okay, everything else that we write inside here is going to be inside these brackets. If I don't close these brackets, I can write a whole bunch of code and then forget how many times I needed to open and close brackets, and the code just doesn't work. It's easier to make sure they're open and closed before I start doing anything. I might also put a return 0 in here. Note that what I have done here, I press tab for this. In gedit, tab is going to give me 4 spaces. I've done this, and this is called indentation. I'm going to talk more about this later. The indentation tells me that something is inside the curly brackets or not. The program doesn't actually care whether this is indented or not, but I as a human care because it's easier for me to read things if I know that something that's inside brackets is indented further in. So it's just easier to sort of scan blocks of code. When I'm at this position here, my code is a functioning program. I mean, the functionality it has is absolutely 0 because the only command it has after it starts running here is the command that says finish. So if I run this now, it'll just go back to my terminal. So nothing will happen. I won't see anything. No particular processing happens. But at least if I was to stop here, my program technically works, right? It technically runs. And it's nice to at least start with it in that state so that when I start adding stuff to it, I know that if anything I've added to it is weird, then that's the problem, not that I didn't start from a state that works. Okay, I'm going to press Control S here, so that's saved at least, so I can, so I've got my file. Okay, so the first thing I did was some comments saying what it is. I would suggest when you've got more time than in a lecture, you would probably have more comments than that. I'm going to use a hash define for our secret number. So the hash define allows us to have a constant. The hash defines go outside the program. So they don't go inside the int main where the instructions are. They go up here with the hash include. Oh, I should have said this when I was talking about these. When we hash define, we do it in all caps. Doing it in all caps reminds us as humans when we use them that they're not variables. Because they're not variables, we can't store values in them or anything like that. They are a value that we can read only, in a sense. So I'm going to make the secret number 7. I'm just going to assume we're rolling 2 6-sided dice, so 7's a decent value to put in there. Okay, so that's my secret number. I've got the main function already. And I might set up some variables here because we're about to grab some information from our user. So I'm going to set up 2 integer variables for the dice that the user is going to tell us about. So declaring an integer, I say what type it is. It's an int. And then I say what name it is. So I've got 2 dice. I'm going to call one of them die1. And I'm going to call the other one die2. It's up to you whether you want to give these a value to begin with. I might just as a pure safety. So I might say these equal 0 to begin with, but I'm going to basically immediately write over that number because I'm going to get my user to give me values for the dice. That's going to happen. A question there. The question was, is there a number that I should use to initialize my variables? Usually, if I'm protecting against mistakes or errors, I will initialize with a value that I think is not going to happen. So if I think my user is going to roll dice, and so it's going to be a value between 1 and 6, or 1 and something else, initializing as 0 might be handy because I could check later for that 0. So I could say, if it's 0, it means we haven't gotten the input properly or something like that. Or if I wanted to be really careful, I could say, let's make it a -1. So it's like, this is going to be really obvious later on in my calculations if it still says -1 when it should have been another number. So by the time I should have gotten a value between 1 and 6 from my user and it still says -1, then I know that something's wrong with my code or something's wrong in the input, or at least, it's given me some information. Okay, so I've got my variables here. I'm already off what's happening in the slides, but it's okay. I'll give you the code I actually write. Then we're going to talk to the user and ask them about their die rolls. So we're going to say, hey, user, would you like to please tell us the information about the die roll? And then we will scan it into this variable. So let's write that. So I've got my variables there set up. I need my variables to exist before I try to scan into them. You can't scan into something that doesn't have memory ready to accept the information. So the first thing I'm going to do is I'm going to printf. Again, note, I complete my brackets before I do anything else in them. It's just sort of this practice that can make things a little easier for you. And I've completed my double quotes as well before I put anything in them. So please type in the value of die1. I don't need a capital there. And so that's just a message to my user. And then I'm expecting my user to type something in there, so I'm going to go into a scanf. So I'm going to scanf, and I'm expecting the die to be an integer. And it being an integer means I'm going to use the %d for a decimal integer. And then, with a comma, I'm then going to need to give it the location of the variable that I want it to put that value in. And that's going to be this and that I was showing you before. die1. So hopefully what that will do then is it will say something to the user, then it will read in a value from the user, and after it's read the value then die1 should have whatever value the user has just typed in. I wonder if I was going to, yeah. Actually, let's then do the same thing for the other die. I might just get a little cheeky here. Control C and Control V because it's going to be very similar. And I'm going to say, now we ask for die 2. And we put the information in die 2. Oh, we got a question over there first. Yep.
What happens when the input's put in? Like, how does it know to subject the input?
Cool. So the question here was, what happens when the input actually goes into the program? When the person types something in and it goes in, how does the program know when it's going to continue or not? The way this works is actually the Scanf. So the Scanf here has been told, I've been given a single pattern for a number. So I could even give it this. If I wanted to, I could give it this, and then this Scanf would keep running until it received 2 integers. But because I say I'm doing one at a time, I'm saying after you've received 1 integer in input, then the Scanf completes and you go down to the next instructions. Yeah. So I think that's... There's no timer. It will just keep sitting there and waiting until it gets the number. Yeah. Well, I mean, I guess there's a feasible timer in terms of like when you're going to turn your computer off or something where it's going to go to sleep. But otherwise, there's no limit to how long it will wait for these. Okay. So this code here should be able to read in 2 values from our user, and I'm going to add a little bit more to this so that we can see what's going on. So we want to calculate the total, which means we're going to want a different variable here for the total, so we're going to store another number. And so I'm going to declare another variable. I should actually put some comments in here. Scan in die values from user. I might even do that. There's a bit of sort of paragraphing that we do to make it easier for ourselves. You can see I put like a spare line in between here, which just gives me space in between the things I'm doing, so it makes it easier to read. And I'm going to calculate and report the total. So if I want the total and I want to store another number, I'm going to make another variable for another number, so int total. And you can see from the names of the variables that I'm using here, they're reasonably simple to understand. Like, we're not going to get mixed up between our 3 integers because I've labeled them really clearly. If I called these A, B, and C, then things could get really, really weird. So int total is equal to the adding up of those 2 values. So die 1 hopefully has a value if we've gotten to here, and die 2 hopefully has a value. So now total should equal the adding up of the 2 numbers that the user typed in. Just to make this safe for us to understand, I am now going to print out the total. I'm going to say rolled, and I'm going to use my printf patterns to send a number back out to the user. So %d, it's an integer, so it's going to have the %d. You rolled this total, and I'm going to put a /n on the end of that one so it goes down to the next line after saying it. Because I've got a %d in there, I need to give it the variable value that's going in, which is going to be the total. Okay, this is good. At this point, we can actually run this and see what's happening. So I'm going to compile this first. This could be where some errors come up. I'm not sure. We'll see how we go. dicechecker.c, the output file for this, I can name it whatever I want. It's whatever program I want it to be. I'm just going to call it dice for the moment. Often we will give this exactly the same name as the C file, but you can kind of do whatever you want with it, because the program is different from the C file itself. Okay, we got no errors there, which is kind of lucky, I guess. Most of the time when we're writing code, this is where the errors first come up, and we're going to try to fix them before we run anything. Okay, if I want to run this, /dice, dice is the name of the program that I've just created. Please type in the value of die 1. Someone give me a number between 1 and 6. 4. Wow, it was like 3 people said exactly 4 at the same time. Another number? 631. Okay, I think 6 just got in first before someone else. You rolled 10 total. Okay, this is a good sign. This means that a lot of what's happening in our program is currently working. And so we're able to, okay, the text is slightly different from what I printed out here, but it's the same idea. So now what we want to do is test this against our secret target. So we're going to start with our if statement and see if things are going to work or not. I am just about to run out of time, but I will, I'll try to get a little way into this anyway. Test against secret target. Anything that I do that's past the end of the recording, which is in about 60 seconds, I will probably record in a video later and just post it up on the webpage so you can see it.